In the second half of Chapter 5, we're going to be looking at two additional calibration methods that we can use. Our typical method of calibration, what's known as just a standard calibration curve, is where we take a sample, or we take multiple samples that we have prepared with known concentrations, and we measure the signal that we get from each of those samples, and that should establish a straight line. And usually that's sort of our standard operating procedure that we'll use for most cases. We'll use that for several experiments this semester, for example, in the labs. But sometimes that doesn't always work. So this gives an example of a specific example. This is figure 5.4 from your textbook, showing that if we have two different ways, or the same way, of measuring the concentration of perchlorate, ClO4-, in groundwater, or in water in general. So for the black points in line, that is reagent water, so that's like what you would prepare in a lab. Whereas if you measure that concentration of perchlorate in groundwater, you can see that the slope of the curve is vastly different. Now, what's happening here is that the matrix, meaning what's present around the rest of your, what the other things that are present in your sample besides just your analyte, is affecting the measurement. And so we can see a very clear matrix effect in this example. So if we, say, prepare reagent water perchlorate samples and do a calibration curve, it's not going to match up with what we'll measure from the groundwater because of the interference of the matrix in the measurement. It's leading to some effect is happening that causes it to change. We still get a linear response, but it's not the same slope. And so we need a different method for examples like this. All right, so let's switch back to where I can write. And the method that we use is called standard addition. And this is again a way to account for the matrix effect. Now, one way to account for the matrix effect is if we could prepare samples that were the exact same as the groundwater in the lab, then we could create standards and do a typical calibration curve. But something like groundwater is not consistent, right? It's a complex matrix, and we can't easily reproduce it in the lab. Things are dissolved into groundwater from the rocks around it, and it's difficult. We'd have to measure like everything that's present in it and recreate that, which is difficult. A much simpler way is to use this method of standard addition. So the idea here is this is kind of like a spike, kind of like a very similar idea to the spike recovery that we talked about earlier in the chapter. We have our sample here. Now I'm showing this as a liquid. This is not just for liquid samples, but it's often what we're measuring in analytical chemistry. So maybe this is our groundwater from the similar to what we saw in the slide. And what we do is we add a small amount of standard, so hence the name standard addition, add a small amount of standard with known concentration. So maybe this is like a 10 ppm perchlorate for the example that we're considering here. All right, so our volume will increase slightly, and the concentration, right, so we have our rainwater plus standard here. Okay, and so the idea is that what we're now going to measure is this change in the signal that we get. And now the matrix is still present, right? We haven't, because we're only adding a small amount, like the volume is fairly small here. The matrix is basically going to stay the same. The concentrations will all get smaller slightly, but all the same things are present. So anything that the matrix is affecting will happen in both the sample and the sample plus the standard. And so the idea is that we can basically use a ratio here to find the original concentration. So let's go through the math of this, of how this will work. For right now, we're just going to consider one standard addition, but typically what we do is we add multiple standard additions to make a calibration curve, and we'll go over that in the next video. Okay, so the things that we need to think about, we'll call X. X will be the concentration of our analyte in the unknown. So Xi is the initial concentration. So this is what we're trying to find. And then once we add the standard, the volume will change a little bit. So the concentration will be a little bit different. So this is concentration of X after standard addition. We'll also have our standard, which is the same thing as X, but we know the concentration here. And that'll have some final concentration after it's been added. And then we'll have our signals. We'll call this Ix is the signal of the initial solution. So like our rainwater, our groundwater in this case. And then there'll be a signal where we'll have the standard plus our unknown. So Is plus X, this is the signal after standard addition. Okay, and so one assumption that we make here, and this is the assumption we often make in analytical chemistry for almost all measurements that we make, is that the concentration and the signal are directly proportional to each other. Or another way of saying this, there's a linear relationship here. So we assume that this linear relationship will hold, and that if we increase the concentration, we'll get a proportional increase in the signal from our instrument or our experiment. Okay, so that means that if we make that assumption, that the ratio of our signals and concentrations should be equal. So if we take the ratio of our initial concentration of X divided by the final concentration, which will be our final concentration plus the standard that we added, right? So those will both be present. That'll be that ratio will be the exact same as the ratio between the signals of before and after the standard addition, right? However much standard we add, the signal should increase proportionally. So basically, that's what we've made this assume this linear relationship, and that means these ratios should be equal to each other. Now the things that we know almost every, so this we will measure. This we will measure, right? Those are the outputs of our experiment. This is the one we have a question mark about, and this value is known as well, right? We know how much standard we added, and we know the volumes involved, right? We have control over volumes in this case. And so the main question we have, right, and this is the, right, Xi, this is what we're after, right? We want to know that. Now, if there's a relationship between these two, then there's only one unknown. And of course, there is a relationship between those two. The final concentration of X we can find based on the dilution equation. So it'll be equal to the initial concentration of X times our dilution factor, which will be how much standard did we add? Or sorry, how much volume did we start with divided by the final volume. Right, and this is just an application of the dilution equation that we've seen before. C1V1 equals C2V2. Right, so we can say XFVF is equal to XIV0. Right, so here, just to write this explicitly, V0 is the initial volume, VF is the final volume, and we'll call VS the volume of standard. So we can say V naught plus Vs equals Vf. I'll just write that again mathematically. If we take the initial plus the standard added, that's our final volume. Okay, so we can make a substitution here, right? Xf here on the bottom is related to Xi. And same thing for our standard. We can also write a concentration there that, similar to here, Sf is equal to Si. This is the concentration of our standard solution. So that's our known quantity, is going to be equal to the concentration, or the volume of standard divided by the final volume. Right, so that final standard concentration, again, this is an application of the dilution equation to find what's the concentration of the standard in the final solution. Okay, so that means we know everything except for Xi. Well, once we know Xi, we can find Xf. So there's one unknown here. So once we have all of this, we have our measurements, we can rearrange this equation to find Xi. And this is the basic idea behind what we do for standard addition. Now this is specific to just one addition, and in the next video we'll look at doing this with a calibration curve of standard additions.